Alright, hello and welcome to the trees slides. You already know trees, but we are going to go a little bit further than we went in CSCI 41. So let us get started, and we'll also relate graphs to trees, those traversals that we just talked about. Those are creating trees secretly, aren't they? So we'll talk about those too. So yeah, let's talk about trees, and this is the general kind of tree. In CSCI 41, I should say, CSCI 41, we talk about binary trees. There are more than just binary trees. Let me show this to you. A tree is actually defined to be a special kind of graph. That's why we need graphs first. A tree is an undirected graph, so there's no arrows. It can move in either direction, right? Parent to child or child to parent. It is connected. There's no dot over here that you can't get to, or some other subtree over here that's like not part of this tree. That's not right. And it also has no cycles. There's no cycles in a tree, right? Normally, we think of these kinds of trees, but there's others as well. So definitely we need graphs to talk about this at all. But yeah, this is like a normal looking tree. You don't have to have just two children. Sometimes there's a root. Maybe you can have three children over here. Maybe you have just one child here. Two children here. That's just a generic kind of tree. And some of them, the ones that we usually care about, have a root, like a starting place. Notice that you can get to every one of them, but there's no cycles. There's no can't jump up here or something like that. There's no cycles. It's connected. It has all these graph things that we like. It's a special kind of graph. So it's not a requirement for trees to have a root, to be rooted trees. The opposite of a rooted tree is one that is a tree that, a graph that is a tree that has no root looks like this. It's just like, this could be a root, this could be a root. You don't pick any special one, you just let it be. And so if there's no concept of a root to your tree, it's called a free tree, right? And a leaf of a rooted tree kind of makes sense. It's like it's at the bottom of the root. It's the farthest away from the root. You can't go down any further. There's a concept of direction. But when you have a free tree, there's no concept of direction. There's no starting point. And so we say that leaves of free trees is just any node that's connected to only one node. So it's like this is a leaf. This is a leaf. Which is technically correct for this one as well. Like this has got to be a leaf. This has got to be a leaf. So these are all like the leaves of the free tree. It's connected to only one node. It's got one edge going somewhere. Okay? So that's the slight difference. Hopefully it makes a little bit of sense. There are plenty of memes. This is a very common concept, of course. I hope you've seen some of these already. But there will be more than that, and you can understand them all. So let's talk about rooted trees specifically, because we probably care about those the most. So let's talk about some terms for rooted trees. Let's remember them. Maybe we've seen them, maybe we haven't. So let's talk about level first. So the level of a vertex, first of all, this is a rooted tree, so I have to tell you what the root is. So here's the root, let's say. The level of a vertex is how far it is away from the root. So the root itself is at level 0, we say. It's 0 distance away from itself. And then all of its children is distance 1 away from it, one node away. That's level 1. Okay? And then, of course, we have level 2, 3, and 4. So those are levels. The height of a tree itself, the height of an entire tree, is the highest level of any vertex. So this one goes all the way down to 0, level 1, level 2, level 3, level 4. This K node is on the lowest level, the highest number. So level 4, that is the height of the tree. All right, so this tree's height must be 4. That's how we define it. It's the largest level of any node. Height equals 4 for this tree. And that's kind of just saying you have to follow 4 edges to get to the bottom. 1, 2, 3, 4 to get to the lowest point. All right. Parents and children, of course. Hopefully we remember these. The parent is the next node upward towards the root. So like the parent of F is E. The parent of E is B. B has no parent. It's the root. And then the opposite is true, of course. It's if you're the parent of somebody, they are your children. So E's child is F. B's child is E. All right? And you can go further. You can talk about grandparents. You can talk about just generic ancestors, right? So every vertex from a node to the root is an ancestor of it. So like K, G is its parent, it's also an ancestor. H is its ancestor, or grandparent or something. D is the ancestor of K. Just as you work your way up, those are all ancestors. All right, and likewise you have descendants. Like the entire tree is a descendant of B, right? D is a descendant of B, H is a descendant of H and H is a descendant of B and D, G is a descendant of all these three, K is a descendant of all of these three. It's just from what perspective you want to think. It's very normal. It's like a family tree, of course. Every leaf has no children, of course. That's what it means to be a leaf. Like you can't go down any further. K is a leaf, C is a leaf. And then you have subtrees, of course. Subtrees is like you pluck out a piece of a tree and you consider it that piece a root, and then you just take the stuff below it and consider that only. So here's like, if you just say, I pick D as the root of my subtree, you are forced to take all of these guys, everybody that's a descendant of D. So this is a subtree. A subtree. You just pick somebody else to be the root, right? It's a tree consisting of that vertex that you want it to be the new root and all of its descendants, right? And one very interesting fact about trees is there's always a unique path. That's key. There's a unique path from every node to every other node. So if you want to move around your tree somehow, like you want to get from F to J, there's only one way to do it without retracing your steps. You have to go up here to the common ancestor and down. That is all you can do. It's the only way to get there. The only way to go from G to I is to go up and around. There's no second option. That's a very powerful thing. That is an important fact that makes it a tree. All right, I think that's everything that I wanted to say on this slide. Here are some questions for you to try these. See if you can get them. So here are a bunch of questions. Please pause the video and ponder all of them, and then I'll show you my answers. Here are the definitions if you'd like to take a look at that just briefly. All right. Which vertices are ancestors of the vertex N? So here's N. The ancestors are the ones that come before it. So like its parent and its grandparent all the way up to the root, and there's only two up to the root, so it's H and A. It's those people. What are the descendants of vertex I? Well, I is just the descendants of somebody is everybody in your children and their children, their children's children, and so on and so forth. So E and F are the two descendants. The leaves of this tree are the ones without any children. So you have the C node, you have the E node, the F node, the D node, the B node. All those guys have no children. That's it. What is the level of a vertex? So this is always level 0 at the root. Excuse me. I guess I'm allergic to this vertex. So this is level 0, 1, 2, 3. That's where D is. That's level 3. Level 3. Okay. Level 3. What's the height of the tree? It's the maximum level. So if this is level 3, one more is level 4. And those are the two nodes at level 4. It doesn't go any further down. So that means the height of the tree is 4. All right. List the level 3 vertices. We just did that. It's going to be D, of course. We just solved that. And it's also I and D together. And draw the subtree rooted at vertex H. Okay. How about I just circle it? It's all the stuff that I circle. There. That's your diagram. With the dotted line. Here is the subtree rooted at H. It's just H gets to be the root of a tree. Just think of it from its perspective. It becomes the root. Forget about these guys. Scratch them out. That's the subtree rooted at H. It's everybody below it, all of its descendants. And then what are the siblings of vertex I? I think you can imagine what that means. It's everybody related along their parent, right? So here's N. Its parent of I is N. The sibling of I must be D. That's only one sibling, right? It's a different child of your parent. That's what it means to be a sibling, right? So that's just normal family tree kind of stuff. And I think that is, that's the idea. So Hopefully that's making some sense. It's all coming back to you. I'm sure you've seen these terms before. We're just hitting them a bit harder and more formally this time. So let's see, was this something I just said? There's a unique path from every node to every other node in a tree, and that's a very powerful feature of a tree. So let me prove that to you. There's a unique path between every pair of vertices in a tree. And we're going to prove this by contradiction. Ooh, so this will be fun. So what that means is we have to assume that this is not true. So assume that there isn't a unique path. Assume that there is like more than one path. So here's how it goes. Assume, well, for the sake of contradiction, if there's not a unique path, then there are two paths. Let's give them names. Let's call one path P and another path Q between two vertices. So that's the opposite of there being a unique path. There being at least two. Let's assume that there's at least two vertices. There are two paths P and Q between vertices U and V, and they're different. All right. So what does that mean? So here's U, here's V, and I'm saying that there's a path. There's a path P to get there, and there's a path Q to get there. Weird. They don't have to look like this. They could like share some pieces. So like this could be the path P, like it goes along here for a while, it veers off and it does that, and then Q, I guess it could have nothing the same, but it could share some pieces of the P path. Sorry, the blue one is the path P, and then the green one will be the path Q. So they can veer off just a little bit. They can share some pieces, but as long as they're slightly different in the end, that's the goal. So this is path Q. And that's what it would look like. Either they go off completely or they share some pieces, just without loss of generality. P and Q kind of look like that. But think about it. Here is where they meet up, right? Either they meet up at U and V and they just veer off completely, or they meet up in the middle somewhere. But here's that middle part. Oops. Like they come together at least at U and V, maybe later and earlier. Okay, so those two places, what are these but nodes in the tree? Okay, and what can you do between those nodes? Move around. Boop, boop, boop. That gets between these two nodes, they're unnamed. And then I can go boop, 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 right back. What did I just do? I just found, like, this is a separate place in the tree. It's supposed to be a separate path. These are different places, different nodes to follow. If I can move around like this between different nodes and get back to where I started, I just found a cycle. Didn't I? If this is possible, there is a cycle in this tree. And a tree, the definition of a tree, is an undirected graph that's connected and has no cycles. So if I just found a cycle in this tree, I have contradicted myself. I must have not had a tree to begin with. So that means that I found my contradiction, and the thing that I assumed to be false really must have been true. Contradiction. I have a tree. I can't have a cycle. Isn't that beautiful? QED. So that means there must be only unique paths between every pair of vertices, because the second you have multiple paths between two vertices, you can find a cycle, and there are no cycles in a tree. It makes no sense. Isn't that fun? All right, let's see here. We're eventually going to prove this. We're going to prove that we're going to prove a very strong fact about trees. If you have a tree with n vertices, n nodes in it, and m edges, then the number of edges is exactly equal to the number of nodes minus 1. Exactly equal. But to get there, we need this lemma. So let me show you the lemma first. Any tree with at least 2 vertices has at least 2 leaves. That's going to build up the power that we need for this theorem. So let me show you how to do it. Again, it's a graphical proof, but I think you can formalize this pretty well, just like you can with this one. Okay, so any tree with at least 2 vertices has at least 2 leaves. All right, so proof. Let's figure this out. We're going to do it by contradiction again. That's an easy way to prove this. We're going to find the longest path P in whatever this tree is. We're going to let U and V be the first and last vertices along that longest path. You can always find a longest path. And we'll show by contradiction that U and V must both be leaves, and that's going to give us at least 2, right? The 2 that we needed for this proof. All right, so that's the setup. And so let's do it. So let's assume that we have some tree. This is the tree that we want to prove that has at least 2 leaves. It's going to work for any tree, of course. And let's find the longest path in that tree. I'm not sure what it is. Maybe it looks all jumbly like this, but there's a starting point and an ending point, and we'll call those U and V of this longest path, all right? And of course, at the tree, you could have moved around in different ways. This green thing is the path P, and it's following some nodes, but the tree is like branching, right? You could have gone off in this place, but apparently it made no sense to do that because that's not the longest path. Only this one from U to V is the longest path. And we're going to prove by contradiction that these must both be leaves, the U and the V. Maybe there's more after it or something. That's the goal, all right? We'll show by contradiction that U and V must both be leaves. So if we're showing this by contradiction, we're going to assume that U and V are not leaves. At least one of them is not a leaf. So assume U and V are not leaves. All right, let's write this on one line. Are not leaves. All right, what does that give us? Well, assume that they aren't leaves, but okay, if they're not leaves, why don't we just go down towards leaves? Because if U and V aren't leaves, that means we could extend our path a little bit, right? Because there's a leaf over here eventually, maybe at least one away, and there's like a leaf over here too. And by definition, leaves don't touch anybody else. There's no cycles, there's no getting at places that we've been before. If these U and V were not leaves, then I can make a longer path, couldn't I? But I'm assuming that P is the longest path. You see that? That's the trick. If U and V were not leaves, then you could like go towards a leaf in the U direction and the V direction, and that would extend the path, right? Maybe you have multiple options. Maybe V has multiple children, and each of them are leaves, or eventually you get towards a leaf. Like that would be a length one more path. This would be a length one more path. If they're not leaves, you could extend it. That would go against the fact that we have the longest path. But then we'd have a longest path. That makes no sense. But then we'd have a longest path. Contradiction. Excuse me. Contradiction. Therefore, U and V must have been leaves, and there's at least two of them. Yay. That's the goal. And this is talking about free trees, by the way, because if one's the root, there can only be one leaf if there's at least two vertices. But in a free tree, nobody's the root. It's just one away. There's only one neighbor, so they're both going to be leaves. That's the idea. So that's that lemma, and this will let us prove that for any tree, a free tree or rooted tree, if you have n vertices and m edges, this is how they correspond. Number of edges is equal to your number of vertices minus 1. All right. Let me show this to you. Here is the theorem. It's an inductive proof. Proof by induction on n, the number of nodes in the tree, number of vertices. Okay. So, let's see. I guess you could do... Yeah, either way it works. You could have multiple base cases. You could do base case n equals 0 or n equals 1. Let me show you both ways, because why not? So we're going to prove that for any tree, here's a tree. It's always going to work like this. Like this is some weird looking tree. There are 1, 2, 3, 4, 5, 6 nodes, and then how many edges? Let's count them. It has to be 5 though. 1, 2, 3, 4, 5. And we're going to prove that it's always going to be one less than a number. All right. So base case. What's like the smallest tree we could have? Base case. I think we could have a size 0 tree, but then you'd have like -1 edges. That wouldn't make sense. Let's just say the smallest tree we'll consider is a size 1 tree. I think, yeah, there's only one real base case here. What we need to show then, that m equals n minus 1, and n is 1 in this case, which is 0. So here is a tree, the only tree of size 1, right, with one node. It has no edges. So of course it checks out. Number of edges is 0. So QED for the base case. And then for our inductive step, what we're going to do is assume that we can do it for a smaller tree and try and use that fact for a bigger tree. All right? And this is where our lemma is going to come in. So inductive step. All right, so we have some number of nodes in our tree that's like k plus 1, right? That's how induction works. What we need to show is that the number of edges in this tree with k plus 1 nodes is equal to, well, it's going to be our number of nodes minus 1, so k plus 1 minus 1, which equals k. All right? And what this is saying, right, that is a tree with k plus 1 vertices must have k edges. That's what we need to show. And this is induction, so we can use the fact about a size k tree. Vertices has k edges. We can use the fact that a size k tree must have k minus 1 edges. Right? That's our inductive hypothesis that we get to use. IH, that is saying that a tree with one smaller number of number of nodes, a tree with n nodes has, well, if n is k plus 1, a tree with k nodes, excuse me. A tree with only k nodes, one less, must have k minus 1 edges. And we'll use that. So here is our tree, all right? Here's our tree, and the goal is we would like to find a smaller tree and like add a piece to it. So like here's our weird looking tree. I don't know what it is, but I know that the size of this tree, first of all, the number of nodes in this tree is more than 1 because I'm in the inductive step, first of all. Okay, the size of this tree that I'm considering right now is greater than 1. So our lemma applies. All right, that's where I'm going with this. So here's my weird looking tree. I know it has at least 2 nodes. All right. Here's the goal. It might find a leaf. There's at least 2 leaves, right? So find a leaf of this tree. There must be one somewhere, right? So find it. Here it is, all right? Find a leaf. Like here's the green part. This is the full tree. You see a smaller tree here? It's everything but that leaf. That's what we want to consider because there's our smaller tree that our inductive hypothesis can apply to. See that? Okay. We are always going to be able to find a leaf in a tree with at least 2 vertices. We just needed 1. And here maybe it is. All right. So here's the setup for the inductive step. Find a leaf. Find a leaf and consider the tree without that node / edge, without the green stuff. Just the rest of it. It's all still connected. It all looks like a normal tree still. Find a leaf and consider. You're guaranteed to find a leaf because we have greater than 1 number of nodes by our lemma. Find a leaf and consider the tree without that node or edge. Without that node / edge. Because it is a leaf. It's like it's got the node and it's got an edge connecting it to its parent or whatever. All right. Here is that smaller tree. How many nodes does it have? It has exactly k nodes, doesn't it? 1 less. Oh, so that means our inductive hypothesis can apply now. Apply it to this tree. What do we get? What do we know now? There's our tree. It has 1 leaf removed. So like chop off. Just for a split second, we'll add it right back, right? Chop off this guy and this guy. Let me draw some better X's. Like get rid of this. Get rid of this. Just for a little bit. Bring it right back. That subtree, right? That smaller subtree without that leaf, which contributed 1 edge and 1 node, that subtree has k nodes. Therefore, by our inductive hypothesis, that subtree must have k minus 1 edges. Therefore, the subtree has k minus 1 edges, and that's what we needed. Because the full tree now, the full tree is n nodes, k plus 1 nodes total. By adding this one back in and this edge back in, I know how many those are, right? It's one more node and it's one more edge. So it has k edges. The original tree must have k edges, which is exactly what I needed to show. Tree has k edges. Yay! And that is QED. That's exactly what I needed to show. We have k edges. We did it. The goal is, I have at least 2 nodes, so that you have at least one leaf, at least 2 leaves. I only needed 1. Find it, chop it off in its edge, consider the smaller subtree. You get by the inductive hypothesis that has exactly k minus 1 edges. Here's the one more that we're adding back with its node. The original tree must have k edges. So that proves our theorem. For every tree, the number of edges is the number of nodes minus 1. That's how it works. Isn't that so cool? I hope that's exciting to you. I like it. It's a fun little proof, I think. So now I want you to try. Here's a proof for you to try. Let me show you some, let me teach you one term though first before I let you try this. This is called a forest. A forest is just a bunch of trees separately, which is a cute little pun, I guess. But a forest is a graph that has no cycles but isn't connected. So it's just a bunch of trees by themselves, but you consider them all at once, like it's this whole darn thing. That is a forest. It's just a bunch of trees together. Okay? That's all. They're just not connected. And there are 3 components in this forest. There's this one, there's this tree, and this tree. Those are called components, right? Here's the proof that I want you to do. Prove that a forest with C components, so like C is 3 in this example, C components and n vertices must have n minus C edges. And assume that n is greater than or equal to C. All right? And my hint for you is, again, use induction. You can use this theorem that we just showed. That's going to be very necessary, right? Potentially. Or actually, no, sorry. It's going to be the same style, but I don't actually think you need this theorem. Yeah, that's the goal. And then the base case will have n equals C edges. That's going to be the goal. And the inductive step will be n is bigger than C. So it's going to be induction on n. Prove that a forest with C different components and n vertices has n minus C edges. It will go very similar to the last proof. You like chop off an edge or something. So think about that. But to be able to chop off an edge, you need to know that you have at least 2 vertices. So how will you show that to yourself? That's the idea. Okay, so assuming you gave that a good try, let me show you how I might prove this. So the base case, we're doing induction on n to prove this. Every forest with C components and n vertices has n minus C edges exactly. So the base case is if n is equal to C. All right. What we need to show is, if you have n C components and n vertices and they're equal to each other, then we need to show that the number of edges is equal to n minus C. And if they're equal, right, that's equal to n minus n or something, which is equal to 0. We need to show that there are no edges at all. Can't have any edges. So what does that mean? Like here are C components. Like there's like 3, 4, 5 components or something. 5 components, 5 nodes. Yeah, of course there can't be any edges. You see that? If they all have to be separate components, you have to have as many components as there are nodes. None of them can be connected to each other. They can't have any edges. So that's easy. Can't have any edges at all. So that checks out. So that's QED for the base case. The inductive step is, of course, harder. So inductive step, you have some number of nodes that's greater than the number of components. So at least you can double up. Some of these actually have multiple nodes in the tree. Inductive step. All right. So n is greater than C first of all. Now, n is greater than C. Let's assume that n is equal to k plus 1, as we like to do. Well, we need to show that the number of edges is equal to the number of nodes minus the number of components. So it's going to be, well, k plus 1 is the number of nodes right now. K plus 1 minus our c, whatever that is, number of components. So we get to use our inductive hypothesis now, IH, on a smaller n. So we can find a smaller forest, I guess, then things would work out for us. We could apply our inductive hypothesis, and what does that tell us? Our inductive hypothesis tells us that if you have a forest with n vertices, if you have k vertices, if you're considering a forest where n is equal to k, the number of nodes is equal to k, then the number of edges, we get to assume that our theorem holds for that smaller number of nodes, then the number of edges is equal to k minus c, because that's our n in this case for the smaller sized forest. Okay? Just assume that c is the same size. So here is the trick. Like, pretend that c is 3 or just some number. If n is greater than c, what does that mean? That means that there's at least none, they don't all look like this. At least somebody has like an edge that actually means something. So there exists a component that has a size that's greater than 1. Okay? There must exist a component. If n is greater than c, there's more nodes than there are forests, or than there are components. Somebody has to be connected to somebody else. There exists a component. There has to be an edge. There exists a component of size greater than 1. By our lemma, you can find 2 leaves. We just need 1 again. So pick a leaf. Get that component, pick a leaf out of it. You're guaranteed to find at least 1 component that has a leaf, so pick that leaf. Pick a leaf out of that component that has at least 2 nodes that's connected to somebody. Pick a leaf out of that component and consider the subforest of everything without it and its edge. And consider the subforest. So for example, like here is our example. Here is a component with at least 2 nodes, and here is a leaf, for example. Here's a leaf. Let's pretend for a second that it didn't exist. Let's chop it off, and here's a smaller subforest with the same number of components, just 1 less node and 1 less edge. So this is now looking a whole lot like our previous proof. So the subforest must have 1 less node, so just k nodes now. The subforest must have k nodes, has k nodes. So by the inductive hypothesis, it has, so by the IH, it has k minus c edges. And we're trying to prove something about the biggest graph with k plus 1 nodes, just add this thing back in. We took off 1 edge and 1 node, just add them both back and you get the original thing again. Adding back the leaf and connecting it up again. Adding back the leaf to make the original tree, original forest, adds 1 more edge. Therefore, the number of edges is equal to the k minus c that we got from our inductive hypothesis, and then we added 1 last edge to make the full tree again, k minus c plus 1, which is k plus 1 minus c, just the 1 moved to the end now. It's the same number. QED. Isn't that fun? So that proves it. We've proven that any forest with c components and n vertices must have n minus c edges. Isn't that lovely? That is the goal. So good examples of induction, I think, for this set of slides. All right, one last one for you to try, and then I'll show you some traversals of trees, or at least remind you of them that you've seen before. So pretend we have a graph G, pretend it's undirected, and it has n vertices and m edges, so some arbitrary number. Prove that if m is less than n minus 1, right, if it's exactly equal, it is a tree, prove that if it's less than that, if it's less than n minus 1, it can't be connected. If m is less than n minus 1, it can't be connected. And here are my hints to you before we start. So for example, like here is, I don't know, here's a graph with, let's say, m is 2, n equals 3. So that's exactly equal. N is equal to m is equal to n minus 1. If m is less than n minus 1, that's like chopping off one of these guys. It's like chopping off that one, and now it's unconnected, right? Same for this. If we had, let's make a graph where it's not connected. So it kind of looks like this. So here are just some examples to get you thinking. So here, this whole thing is one big graph. So the number of nodes is equal to 8. The number of edges is equal to 1, 2, 3, 4, 5, 6. So it's less than the 7 that it would have needed to be. Like if it were 7, we could have connected it maybe. Why is that? Why is that the special number? So try and see if you can use the fact that trees have exactly n minus 1 edges to help you prove that this is going to work. And my next hint for you is use proof by contradiction. Right? So if m is less than n minus 1, like assume that it is connected in your proof, and derive a contradiction from that. All right? So give that a try, and I'll show you my way. I hope that was a fun one. It's proof by contradiction, which is always interesting. So proof by contradiction. All right. Assume this, right? If this is true, then G is not connected. So assume we have this, and assume it is connected for a contradiction. Assume m really is less than n minus 1, and assume that G is connected for the sake of a contradiction. There's always a way to get from anybody to anybody else. All right. Let's see here. So let's see. Let's think about cycles as well, because you could totally have more edges. If G has any cycles, you can take away edges until there are no cycles. And this is going to be the key piece. If G has cycles, you can like start chopping them off. So like if you had this graph, this has a cycle, n and m are equal, you can just chop this one off, break the cycle somehow. So if G has cycles, you can safely take away edges and keep things connected. Like it's still connected even though I took away that cycle, right? If G has cycles, you can take away edges until there are no cycles. Why do you think I'm worrying about cycles? It's still connected. It'll still be connected if you do that. The hint is all about trees again. Connected. What do these words mean? Alright, so if you took away some nodes because of cycles, you got rid of the cycles, you have just made a tree with a certain smaller amount of edges. So like, let's see here. You had your m, it was less than n minus 1, and you threw away some extra edges. Maybe none. So you have some new m prime. That's the new number of nodes in your cycleless graph. It's still smaller than n minus 1 though. Okay? What is a tree? Where did I put that? A tree is an undirected graph that is connected and has no cycles. That's where those words are coming from. That's where I was going. All right, what does that mean? A tree is a graph that is connected and has no cycles. I have just transformed this graph that I had with this number of nodes into one that is connected. It's still connected, and I also chopped off any cycles. You see that? I'm allowed to do that. I've potentially lost some extra edges, I'm not sure. So what I just made out of my G, maybe it was a tree, maybe it was already, maybe I didn't need to chop anything off. So G, either originally or after I got rid of any cycles, G now has no cycles and is connected. G is a tree. Right? So, right, every tree, that's the definition of a tree, right? A tree is a graph that is connected and has no cycles. We've proven exactly how many edges a tree must have. Exactly this many. We've just shown that we must have a tree right now. So G must have exactly n minus 1 edges. And that's a contradiction. Because we are assuming, well, however many it has after we chopped off any cycles, it has strictly less than n minus 1 edges. It's supposed to have exactly n minus 1 edges. And those two facts are contradicting each other. And so we have just shown that if you have a smaller amount of edges than n minus 1, it is impossible for G to be connected. The smallest number of edges to still be connected is a tree. Every tree has the minimum number of nodes. You chop one off, it's unconnected, disconnected. I hope you see that. And we've just formalized that. Pretty cool, huh? So yeah, that's the last like hardcore proof of the day, I think. I just want to talk to you about some tree traversals now. So just like for graphs, right? I think we've seen this in CSCI 41, it'll just be a review. But we always like to go through all the nodes in a tree for some reason or another. Like we want to print them out, we want to process each of them somehow. And you have options in terms of the ordering, right? You have to decide which order you want to visit all of your nodes. And you have similar concepts to like depth first and breadth first, don't you? The ones that go deep first are either pre-order and post-order, all right? Let's think about that. So pre-order traversal is you visit the root first. First of all, these names, pre and post, it's saying in what order do you visit the root. So pre means first. Pre means visit the root first, then recursively visit the children. This is the pre-order function body. So like you're calling pre-order on some vertex of your tree, some node, you process it, like print it out, do whatever you need to do, and then you pre-order, you recursively call yourself on every child after you've processed your own self, okay? That's what pre-order is all about. Post-order, I think that's the more similar one to DFS for graphs. If you do post-order on a tree, it's visit your children first recursively and then visit the root. So the processing is after rather than before. So it's recursively post-order every child of yours and then process yourself. So that's what post-order is all about. And let me show you what's going on here with all of those. But pre and post is all about in which order do you visit the root. Pre means root first, then children recursively. Post means children first recursively, then visit yourself. All right, so here is my example tree. The root is up top as usual. And let me give you the pre-order and the post-order traversals of this tree, starting from the root, of course. So pre-order. I'll kind of draw it for you. So I would like to start from the root. So I'm going to call pre-order on the root node, the D node. Let me show you how that's going to work. So pre on D is what I call. Okay? And so what happens is we jump to the body, we process ourselves, so like we're printing it out, we're going to visit ourselves first, so visit the D, that's the order. And then, so the pre-order is always visit the root, and then recursively visit the children. Recursively visit the children. In some order, usually you do it from left to right. So we're going to make a recursive call to both G and B, right? We have to pre-order. We're in this for loop. Call pre-order on all your children recursively. So G is the first one, like that's the left child, so let's call pre-order on G now. It's a recursive call. So we're not done traversing D, because like we still got to go to B through D. We're going to the left, and it's always pre-order. So visit yourself, you just visit the G. Now we're in pre-order of G. So that's the next thing we visit. and then you recursively call yourself on all your children. So pre-order your children recursively. So in order, like pre-order C, then pre-order E. So G is going to call pre-order on C. And again, it's always visit the root and then recursively visit your children. So visit the root, C. It's always, this is the root of our subtree now. That's what I mean by root. And then there are no children to C, so it's like that returns. Okay, so we're back down here. And now we're back pre-ordering G. We just visited the C. We're like stuck in this for loop, right? We're visiting every child of that node G. So we still have E to visit. So we're going to pre-order E. Pre-E. And then that involves, well, okay, visit E, then recursively visit its children. So that's the order. There are no children. It's done. Pop off. And also that finishes visiting every one of G's children. We can now go back to the original call to pre-order. Pre-order D. And pre-order D was waiting to visit the left child. It has to visit the whole subtree. And then now it's ready to visit B. So it will visit, remember it's waiting in this loop. Just visited one of its children, it needs to visit the other now. So it's going to visit B. So we call pre on B. And then, of course, it will visit itself. B, all of its children, there are none. It returns. D is finally finished visiting both of its children, and so it returns 2. And so this is the pre-order order, D, G, C, E, B. All right. Post order is all about the opposite kind of post order. It's visit your children first, then the root. Children recursively, then the root. Okay? Let's watch the difference here. So we first call post again on the root, post on D, and it's always, all right, recursively left, right, then root, left, right, then root, left subtree, right subtree, then root. So all right, now we're calling post on the G tree. We have not printed anything out yet. We haven't visited anybody. Post on the G. Then, all right, it's always left, right, root. So post on C now. Again, we haven't visited anybody yet. It's always just get as deep as possible first. So that's very similar to depth first, yeah. And now we're on C, left, right, root. Visit your children, none. All right, now we process the root finally at the end. So here we are ready to process our first node, and that's the C. So the C is the first thing printed. All right, and then we return from there. We return, and so we're back in post of G, which is working on visiting all of its children before the root. So it visited C just now. It needs to visit E still, and then it can visit itself. So we're going to call post on E. And that will go left, nowhere, right, nowhere, visit itself. E. Cool. And now it's done. And now we're also done with visiting all of G's children. So we're back in G itself, and we're ready to process it. So now we're on G. And now it's done. Ooh, now we're back in D. It was working on going left, right, root. Or just all of its children, then the root. You usually do left, right. So we're up here in the call to post of D. It visited the left. It still needs to visit the right. And then it will visit itself. So post of B. And so it visits left, right, all of its children recursively, and then itself. It is the root of its own subtree, then the B. So that's the order in which we see the B finally. Then it's done. Then we're back in post of D that, well, it visited the left, it visited the right. It's finally ready. It was waiting for so long. Right here in this loop, it is ready to process itself. It is seen finally, D, and now it's done. So that's the difference. Post order is very similar to depth first. You see that? Very, very similar. All right, so that's pre-order and post order. Please yell at me if you have any questions about this stuff. Now let's move on to in order and breadth first. There is a breadth first for trees too, if you haven't seen that before. So in order is an ordering that only works on binary trees, and the point of it is there's an order to your trees and like processes going in the middle. So visit the left, then yourself, then the right. And what that will do, assuming you have like a binary search tree, if there is a real ordering, so like here's an example binary search tree, 27, 35, 58. if you call, then I encourage you to try this, it's going to plop everything off the way that it visits. It's always left, root, right. So it's like goes down, visits left, which involves visiting left, then root, then right. So 27, 35. And we just did the left and the root. And that was the left of the 42, so we just did the left. Now we need to do the root, then the right, so the 42, then the 58. 42, then 58. And so it comes up with the ordering that is perfectly sorted. It's called the in-order traversal. It only works if there's a binary tree. There's a concept of left, then yourself, then right, because otherwise you're not sure, like, where do you come in? In-order only works for binary trees. Pre-order and post-order, I thought of it in terms of left, right, and root, but honestly it works for anything. So it's just like process yourself before you iterate through all of your children. Maybe there's 50 children, I'm not sure. In order only, though, works for binary trees, and breadth first works for any kind of tree. It's the exact same algorithm as for graphs. It's just you're starting at the root node this time, and you're making your empty queue, you're pushing to your queue, and then while it's not empty, process the front thing and push all of its children. That will get you breadth-wise first. It will like visit all the things at this level, then at this level, then at this level. All the things of distance 0, 1, and 2 away. All right. So let me show you the in-order and breadth first traversals of this tree. So for in-order, there's a reason I made it a binary search tree. It actually will look normal. But you can do an in-order traversal of any weird-looking binary tree. It doesn't have to be sorted. It's just the in-order is always about left first, then recursively visit the left, then visit the root, then recursively in-order the right. All right. So with that in mind, let me just do this quickly. We're calling it on the 7 node. It's going to recursively in-order the left, which is going to recursively in-order the left, then the root, then the right. So 1, 2, 5. So that was the left of the 7. Then we have the root of the 7, which is the 7 itself. And then it can recursively visit its right, recursively in-order its right, which will do a left, then a root, then a right, so the 9 and then the 14. All right, I encourage you to convince yourself that that is the ordering in which it's going to happen. And then BFS, I think you understand from the previous slides what's going to happen. It's going to like start off a queue with just 7 in it. That's going to be the first thing that's visited. Then it pushes the 2 and the 9 in that order because they're going to be popped off in that order because the things in the front are going to be popped off first. And so you visit the 2, the 9's still sitting on the queue, but you add 2's children after the 9, and so it's going to go in this way. It's going to be like boop, boop, boop. Everything 1 away, then 2 away, 1, then 5, then 14. I encourage you to run this. Try it yourself. Prove to yourself that it's going to work in this order. It's going to visit the 7, then the 2 and the 9, then the 1, 5, and the 14. It's like slowly making its way down the tree. It's not going deep. It's going breadth-wise as fast as it can, all right? And that's very different from post-order. That's going as deep as it can, right? As deep as possible before it like even considers that root. The root's last in post-order, isn't it? Definitely going to be first in BFS. All right. So yeah, this is the root of the tree, by the way. That's very important to say. If we are happy, please yell at me again if you have any questions about this stuff. But I have one last just silly example with Racket. I think I've made this tree for us. I'll show you what's going on. I'll show you a few algorithms. So here's a few of these trees. Here I've made this CDGB-CE tree. It looks like this. I've used this representation. So I made every tree node has a data and a left and a right. And here I am making a bunch of tree nodes, essentially pointers. Like here's the C node. It's a tree that holds the C data, the symbol C, and it has null left and right children. Same with E, it's a leaf. Then G holds, it's a tree with the G node, G data, and then the C and the E children. And that's me building this tree. That's tree 1, we'll say. And then tree 2 is this one with numbers, so the 1, 2, 5, 7, all that stuff. The root is, of course, 7. Tree itself is that root itself. And then, like the 7's children are the 2 node and the 9 node, which are made up like this, and like here are the leaves. It's all very similar. But here are the implementations of these things. Like, yeah, the pre-order. The pre-order is always going to match either the empty tree, which is null means the empty list in Racket. So if it matches the empty list, then do nothing. That's that case, just do nothing at all if you hit the empty tree. But if you have an actual tree somewhere, if it's non-empty, to pre-order it, you're going to process yourself, which is going to be essentially print yourself. That's how we'll process things. Then you're going to call pre-order on your children. So you got the left and the right for every child, call pre-order. When you have just 2 children, if it's a binary tree, just pre-order the left and the right. Isn't that nice? Post-order is the same. It's going to be empty tree, do nothing. Non-empty tree, process your children, then yourself. So left, right, you, process your own data. In order is the average of the 2, right? It's empty tree, of course, do nothing. But in order is going to be your left, yourself, then your right. So recursively go left, process yourself, recursively go right, in order, and that's that. There are queues in Racket, but I didn't want to get into that. So yeah, this is just all that stuff in a different language. So here it is, exactly as you would expect. So here's the pre-order of that first tree, which is exactly what we came up with, DGCEB. And I encourage you to like make your own versions of these and like print out like I just got called on this node. I just got called on this node, so you can watch the stack grow and shrink like I was drawing it here. So DGCEB for the pre-order, CEGBD for the post-order, there it is, and for the in-order on the number tree, it's going to be everybody in order. That's why it's called an in-order traversal. It's kind of meant to be used on a binary search tree where you do have that ordering, that strong relationship on what is to the left of you, what is to the right of you, things like that. All right, so here's some non-C++ code. I have the utmost confidence that you could implement this in C++, so that's why I'm expanding your mind and showing you it all in Racket instead. So yeah, I think that is everything that I wanted to talk about for this lecture. Yeah, we'll stop here and we'll come back and do more cool tree stuff next time. I'll see you then.